coffee up there? Okay, I'm not going to wait too much. No, I just wanted to wait.
Say something. Hello.
Can you hear me? Yeah.
Hello.
Right, so it's with great pleasure that I give you Nick Colstrong. Nick, if any of you don't know, is a fellow of the Royal Astronomical Society, and he has been he has published on lunar gardening, for example, and he's actually, you were teaching history of science, weren't you? That's what you were doing, and he has a very interesting take on life. And less than that. So yeah, Nick, a quick 10 minutes on the heartbeat of the sun.
Let us focus our minds upon the majestic heartbeat of the sun. As Piers has told us, the Hale cycle is the magnetic cycle of the sun. That is the 22-year cycle. Okay? And Lucy just mentioned the Maunder minimum. That was 3 complete heartbeats of the sun. Heartbeat is this 22-year cycle. And it went silent for those 3 heartbeats. And that ended around 1717. Okay? As a period just after sunspots had been discovered, when they virtually disappeared from the sun, and that coincided with the deep cold that was experienced. And there's a question now: are we going into another such minimum, another such colder age? And that brings up the huge question of: can anyone predict what the sun is about to do? We are now waiting. We are now waiting. Now, will the new sunspot cycle start up? 2019. It should have begun by now. Shall I just pass this round? Nice graph of the sunspot cycles. And permit me to suggest that next year's EU conference there'll be no more vital question to debate than whether this new sunspot cycle has started, and if it hasn't, is there a new global epoch of global cooling coming in, and what is this cycle? I want to argue here that there's no better way of refuting the official image of the sun of a nuclear fusion reaction at the centre than this heartbeat. Well, what is the Hale cycle? For centuries, people have known what the sunspot cycle is. Sunspots maximise every 11 years, and as they maximise, they're pulled towards the equator. It's a mysterious process, or butterfly effect, a certain symmetry above and below the equator, and sunspots tend to go around in pairs with magnetic loops, magnetic plasma coming in and out, magnetic fields coming in and out, and there tends to be a certain symmetry in north and southern hemisphere of the sun of these pairs of sunspots. As they go round, we see them every 27 days. But what is this cycle? Can one explain it? Well, the explanation has to involve what happens with the 22-year cycle, which is only discovered in recent decades as the SOHO satellite was sent around by astronomers. You notice, and that they discovered a huge north-south magnetic pole cycle, magnetic poles of the sun, northern sun. A huge magnetic field builds up, and it's out of phase with the sunspot cycle. So now, when the sunspots are minimum, they've vanished, the north-south magnetic field will be maximum, right? Now that, next few years, it will fade away, that magnetic field will fade away north and southern poles of the sun, and as they fade away, the sunspots will grow, normally they will grow. So you've got a pole process, the magnetic field, an equatorial process of the sunspots. Then the magnetic field will start to grow again, but reversed. So it was the North Pole, it's now the South Pole. And it will grow up again, so 11 years later, you've got the same strong magnetic field, North and South Pole of the Sun, but reversed polarity. Do you notice astronomers never talk about this? They've discovered this stupendous process. I mean, Earth reverses its magnetic polarity every, 50,000 years or 100,000 years, and the Sun does it every 11 years. So it's by contemplating, by looking at that the reversing of the north-south magnetic field sun, that we understand that the basic cycle is 22 years. After 20 years, it comes back to the same magnetic pole position that it was 22 years ago. And during that time, you've had 2 lots of sunspot cycles. Okay? Okay. Now, astronomers, obviously we all know, they want to believe there's a fusion reaction at the centre of the sun. And we're all familiar with the tortured logic whereby they, first of all, they couldn't find any neutrinos, and then finally they think they found some, and the neutrinos change flavour as they come towards us from the sun. Now, ordinary people are never going to buy this. It's always too unreal. Particles without mass changing their form as they come towards us from the sun. This is tortured logic which ordinary people are not going to like. Okay? Now, the ordinary man in the street remembers from his science class that heat destroys magnetism. The sun has got something unknown on Earth, a self-reversing magnetic field. It's something we cannot really imagine, can we? Everyone says, well, it's a mechanism. We can't imagine a mechanism, can we? Because it doesn't exist on Earth. A self-reversing magnetic field. That's what the sun has got, somehow at the centre of the sun. For me, last year, the most important words were while saying the centre of the sun is cool. Okay? Now, I think for the ordinary man in the street, you cannot believe in a nuclear fusion reaction going on inside the sun if you've got a vast magnetic field going right through the centre of the sun. And somehow that is the heartbeat that is able to reverse itself. However it does that is somewhat organismic, isn't it? It's something to do with the sun as a whole, especially when we factor in the way the sunspots are reacting. Scientists conjecture about magnetic loops or some magnetic tubes that link together the sunspots above and below the horizon, above and below the northern and southern hemispheres of the sun. So something, whatever is going on inside the sun, it gives some magnetic continuity to this interaction which between the magnetic fields and the sunspots. Now, everything I'm talking about is magnetism, and it's not hard to comprehend that this is immediately relevant to electric universe theorising, and obviously it is likely to be explainable in those terms, if we can explain it. That's pretty obvious, isn't it? And it's pretty obvious that the ordinary, that the astronomical model developed by great astronomers like Fred Hoyle, it just isn't going to do it. It just won't ever be credible. I'd like you to imagine, astronomers always have this kind of stiff upper lip, oh yeah, of course, our theory is one, you know. They put up abstruse mathematics that nobody can understand, and have very powerful telescopes, you know. I want you to try to imagine, just a TV programme, when they're having to admit that they don't know what makes the sun shine. Just try to picture that, right? You know, frankly, frankly, it's got to be, you know. Frankly, our theories have gone up in smoke, you know. We really haven't a clue, you know. I mean, the authority, sensible authority that astronomers have come from this, we can explain what the sun shines. And in a sense, that's the one bit of astronomy that's of real importance to ordinary people. Can you tell us what the sun does? You know, can you tell us what makes the sun shine? I feel that what Plato said, wonder is the most important thing to acquire real knowledge. Wonder, and you start off by admitting we're foxed. It's got us foxed. You know, people. Old books used to say with great confidence coal was burning up in the sun, and now they say it's a fusion reaction burning up inside the sun. Let's just wonder and look at the way this heart beats. Everything that happens on the sun follows that heartbeat. The solar flares, the chromosphere, the photosphere, the corona, it all pulsates to that 11-year cycle, which is strictly speaking a 22-year cycle. It's somewhat biological. It might be quite mystical. The heart centre of the solar system, maybe it has some mystical meaning, I don't know. But I'm just saying, in terms of and also analogy with the heart, the 4 stages of systole, diastole, heart process. I'm just suggesting that if we go through this cycle, it shows us something the Sun is doing that is obviously, very, very obviously incompatible with the accepted astronomical theory. And I'm also suggesting that if we are at this very key point, I'll just read out the Russian prediction, then there's possibly a lot of media mileage in this. The Electric Universe is looking at the way that the solar pulse has gone silent, or is going to go silent. It's Professor Valentina Zarkova is predicting a grand solar minimum, which I think Piers is echoing his prediction.
Oh, that's good.
So the question arises, how do you do it? And so there are longer solar cycles. It was 300 years ago the Maunder minimum ended, 1715, and I'd like to hope, if we want to imagine people being happy, instead of being endlessly given fears, that we have a futurology departments which make predictions based on these cycles of the Sun and Moon. There's the basic solar 11 and 22 year cycles, which often blend with what people call the El Nino. There's an El Nino cycle, which people often think might be a solar cycle. That's lots to do with fish and climate, isn't it? Mm-hmm. And then there's a lot of other prediction to do with the lunar node cycle. 18-year lunar cycle, and 19-year half that period. A whole lot of things like abundance of fish in the oceans. I think a futurology department can use these fundamental cycles, and as Piers has shown, this is predicting the future, the rhythms of the Sun, which do not spell eco-doom. They invite us to predict, just like in the Old Testament with the Joseph story. We have a prediction of famine and abundance, and therefore that is one way in which astronomers can be of practical use to people. So I suggest this heartbeat of the Sun is a subject that will be respected by ordinary people in a way that the very abstract theories of modern astronomy can't ever manage. Okay? So, yeah, I think that's it, yeah.
Fantastic.
Invite some questions. I just have a question about the numbers and whether the 22 years or the 11 years relates to 365 days of the year, or how does it fit in the maths or the numerology of it? Does it have any relationship there?
Not that I'm aware of, no.
Okay.
No. Yeah.
I hope this ice age, this mini ice age, won't come. because no, it's real hard to say. On Earth, every time when we had warm weather, there was culturally a high point. That was in Roman time. That was even before that. Always when we had a high, it was good. People today, they said yes, it's warm and climate warming and all this stuff, but it's a thing that warm periods were good, were culturally the high points in human life.
Right.
And I hope it doesn't fall down.
That's not quite true. That's not quite true, Will. The Dalton minimum was a pretty productive time. And the Maunder minimum was also, the 17th century was a very productive time.
Which one?
Well, both the Maunder and the Dalton.
We had the 30-year
was crop failures as well.
Yeah, crop failures, but we had a lot of inventions.
Frozen and it was
You had the birth of modern science.
You had the birth of modern science.
I didn't even know the whole damn thing.
Yeah, but
Right.
we lost a lot of people. I say, stay with things, a lot, thousands of people, they were dying and they were war all over.
But you have people die with drought. You have people die when there's too much heat. But in terms of creativity, in terms of human creativity, the coal period brought a lot of creativity. The 17th century, a lot of the science we're talking about started in the 17th century.
Yeah, but it has to do because there are some people they try to go out of this period. That's true. That some but for the people, for the regular people, it was a disaster.
Yeah, right,
Agricultural productivity went like that.
Yeah.
But it only varied on certain
that's true.
years. Some years were much worse than some another.
There's
It
more
wasn't
variability.
uniformly bad. That's
Yeah,
the
that's
one.
fine.
I'm just quite curious as to the phenomenon of ice ages and how it correlates with the Proto-Saturn, you know, the Earth's extraction from that environment. And we have these records of where it sort of peaks and troughs over these alleged millions and millions of years. And I just wondered, in fact, given the rise of the idea that mountains can be risen in, you know, seconds or whatever due to catastrophes, and I was just wondering if ice ages are predominantly, rather than a cyclical thing, arisen through catastrophism, and if that can be shown, or if that's completely proven that the correlation between sun cycles actually does, if it's actually cemented that as a phenomenon creates ice ages or interglacial.
Eduardo Cardona has researched that extensively, the problem of ice ages, because you have the conflicting requirements of a lot of heat to evaporate all of that water, and also intense cold. And the cooling had to happen catastrophically, because you get these creatures that were eating buttercups or something, and the next minute they're frozen stiff and preserved.
No, there's a lot of questions.
Yeah, so we have a tendency to try and this comes from the uniformity idea of inventing cycles or looking for cycles when it just assumes the uniformitarian principle. We've always orbited in the same orbit and this kind of thing. The other thing I think is to do with the heartbeat, and that is that Don Scott has shown how the magnetic field varies, and even Christian Birkeland with his Torella experiment showed how the discharge activity from a plasma torus around the Sun, which was imaged in ultraviolet by one of the spacecraft, I think it was SOHO, as the energy density in that plasma torus rises to a peak, it begins to discharge to the body, and it does so starting at the higher latitudes, and as the intensity increases it moves progressively towards the lower latitudes, and it mimics entirely the sunspot cycle. So Christian Birkeland in 1900 or thereabouts was actually performing experiments to demonstrate how the sunspot cycle works.
How did he get an 11-year cycle out of that? Or he just fitted the data to
No, he just showed that you can get this
you could
effect.
get that effect.
So he explained that effect. And then Don Scott, in his book The Electric Sky, has shown how the circuit works and how the magnetic induction from that circuit works. So what we've got is a varying DC, like the old chokes that you used to get in radios, to try and smooth out the variations.
I think that's brilliant. We ought to go into that more.
As for the cycle time, people have looked at maybe it's to do with the sun moving around the Barry centre of the solar
there's
system.
loads of stuff we've done.
But that is surely irregular. That will depend on big planets like Jupiter.
That's right.
That is cyclical.
There's no regular period of moving around the Barry centre, is there?
Well, I think Jupiter is
But the Barry
the
cycle,
key
there's
player.
loads of regular periods.
Also, you've got to
It's a
think,
bit like the Jupiter period of 12 years, but
Yeah.
it really isn't quite, is it?
yeah, you have to look also that the solar system looks a bit like the old vacuum tubes, with the planets being cathodic or electrodes, sorry, in that circuit, and they may modulate to some extent what's going on in the sun. The other aspect is that all circuits have resonant frequencies, and it may be that our particular Birkeland current that stretches out beyond the IBEX mission's neutral atom ring has a natural cycle somewhere in that vicinity. I tend to think that's the most likely thing.
Oh, right.
And there's one more, which may give you a different cycle, and that's the effect in these long circuits, that you get Alfvén waves in the circuit. so they can also modulate. So there's a lot of opportunity in the electric universe model to begin to explain them. As for predicting what the sun is going to do, it's been found that this ring, this ibex ring, varies in intensity, and that may precede.
What's it? Ibex ring?
You know, that ring that surrounds the solar system beyond the heliosphere at some distance, which is our connection to the galactic current, varies. Now, it should vary in advance of changes on the sun, so we may be able to predict solar activity based on looking at this ring.
Right, okay. Yeah, thank you.
No more?
Any other questions? No?
Well,
No, that's
I've got to follow on from this. We still got time for my section 2.
Yeah, let me say that Piers, I was in the Green Party for many years. Piers gave us a wonderful new 21st century philosophy of eco-optimism, that CO2 is good for Mother Earth,
Yes.
and the more we produce, the better it is. The more there's more green vegetation on planet Earth.
I like
Recent decades because of the CO2 that Homo sapiens has been producing, and this is so different from the usual green message, which loads you up with guilt and blame, and tells you not to do stuff, and that's what we used to do in the Green Party, you know. And I think Piers got a marvellous new eco-optimism message. So,
So I'm now an eco-optimist. Wow. As vouched for by Nick Colstrom, but in the mainstream media that means the end. Doesn't matter, I'll accept it. Yeah, I think before I go on to this cosmology stuff, just I think, you know, what Walter's been saying is very important. You see, all these cycles do follow from our weather action theories, and they're mostly involving planets. So, I mean, it's not only the planets, there's the moon and so forth. So we can predict the solar cycle accurately from certain planetary ideas. And then Walt says, oh yes, but it's this resonance of this distance, you know, to the ibex. Well, okay, but all these things are connected. You see, the planets might be in a position dictated by that, or that might be there in a position dictated by planets, and once they're all connected. Some things we did years ago in weather action, we found that the sunspots, when they appear, they're not random. A new sunspot likes to come where there's already sun. You know, they don't come scattered at random. I'm not talking about latitudinally, where they, you know, sink, but around the belt, they're not random at all. And that is very important. So the points that you know, was making, we will follow these up. Now at some point there will be some presentation I'm going to give, because we can explain just about all these cycles in a certain model, i.e. the 7-year cycle, the 2 and the 3rd year cycle of the quasi-binary oscillation, the 7-year cycle of 3 times those, El Ninos, La Ninas, and all that stuff, you know, falls out of what we do. But it's not a complete theory because of the clearly connections with the ibex, etc. So we'll come on to that someday soon. All right. Now, if I may, then I'll go. Oh, also, solar cycle 25, the next one. It actually has started just 2 days ago. There was a new sunspot. That new sunspot was not from old cycle. Officially, well, they say it's his new cycle because it's switched the other way and it's a much higher latitude. That doesn't mean solar cycle 25 is going to get big. No, that might be the only star sunspot in it, who knows? But there is something going on now which is the beginnings of solar cycle 25. I myself think there will be a moderate solar cycle 25, but not my moderate, I mean a small one, probably less than 24. And I would say on this using of cycles in the past to predict the future, then be very careful. Because although I use them, you still got to be very careful. You see, Zarkova's Zarkova, where's she from? Belarus? Bulgaria, one or the other. She's a mathematician. She's not a physicist, nothing wrong with that. She's used standard mathematics, you know, multi... whatever. Well, it's like Fourier analysis, basically. You look at data. She's found a very good way of looking at the data on the sun, using the one magnetic field vector and the other magnetic field, looking at them separately, and when they're in harmony you get lots of sunspots, when they're not you get weak. And that's great, but she's only got a certain amount of data. to project forward, and to use that data to project the lengths that Nick wants to be projected for is I think, you know, it's a step too far, frankly. She's done extremely good work, but one, it's not physics, two, it's presumptive. Okay, now, can I go on to the next one? Right, we're now going to move on to, seamlessly, into the convergence of different theories of large-scale structure of the universe. And I did this at Caterham a week ago because this was going to be a sort of warm-up to here, and it was useful to deal with things. And so I'm applying 7 tests to 5 theories. Okay, and they're interesting. And the curious thing is, you get kind of, well, they're all explaining reality a bit, and I would say, look, don't worry about it. I mean, none of the theories you've got are absolute explanations of the universe. Of course they're not. So they're all aspects of reality, but the fact they're all coming up with something means there's partial truths in all of them, probably. Now, I think the electric universe approach is the tops, but, you know, there's still work to be done there as well. And how it links to the others is the question. So these 5 theories, I'll list what their names are, and then we'll go through them. There's the Higgs-Kibble superstring theory, Einstein A, Einstein B, Mike McCulloch quantized inertia, who came here last year, and electric universe. Right, now, and I'm going to ask the questions, do they have a dark matter problem? Do they have galaxy angular momentum problems? Do they predict the sizes of galaxies? Do they predict the line structures of galaxies in the universe? Do they predict voids? Do they abide by Mach's principle? And do they have a black hole problem? So there's plenty of problems there to be dealt with. Okay. Now, the Higgs-Kibble theory, that's the first one I deal with. I did work on this myself and wrote a paper on it about galaxy formation. Now, the idea of this is the very early universe, I don't know if, is this all right this side? Yeah. Very early universe was like a Higgs-Kibble, super duper heavy, dense field, a vector field in different directions. And these vector fields had edges, like a domain theory of magnetism. There's going to be planes where they meet, right? So that gives you planes of activity or condensation or something. And the planes cross in lines, so you get lines. And when it all expands and the Higgs field kind of collapses, you're going to be ending up with these lines, the remnants of planes, and then there's lines. The lines then crash into each other, and they form loops. And the loops will be thrashing around with a certain amount of angular momentum. So the loops could be, you could have the right number of loops, and a friend of mine, Neil Turek, asked me, "Chris, could we have the right number of loops to do?" Well, he asked me, how many galaxies are there? I said, I told him. He said, oh, well, that's nice. We could get that number of loops out of the theory. Now, you know, he had to choose a theory to get the right number of loops. Okay, but he got the right number of loops. So, roughly, you know, 10 to the 11 galaxies. I've got to get this right, actually. Yes, it's 10 to the 11 galaxies in the universe, that's right. And each galaxy has also got 10 to the 11 stars. Or 11 to the 11 if you like to play with dimensions, and 11 to the 11 is roughly 10 to the 11. Okay. So the Higgs-Kibble theory of superstring loops crashing into each other can give little loops which can then be attractions for matter and turn into galaxies. And they can have, roughly speaking, the right angular momentum, as I showed when I produced this paper, which gave a new view of the Hubble spoon diagram and turned it into, the Hubble tuning fork diagram turned it into a Hubble spoon, as I called it. And I've got copies of that if people want. Now, that theory, did it have a problem and require dark matter? No, it didn't. Did it give galaxy angular momentum? Yes, it did. Very good with that. Did it predict galaxy sizes? Well, partially, because, you know, the best loops to get the right numbers give roughly those sizes. It definitely gives lines, definitely gives voids. Did it abide by Mach's principle? Mach's principle being that the distant matter of the universe defines the local inertial frame, i.e. the non-accelerated frame of inertia, okay? That's what Mach's principle is. And in my opinion, nothing that, if any good theory's got to satisfy Mach's principle. So, yeah, probably not. Maybe it did, maybe it didn't. It wasn't a problem that it could deal with. Did it need black holes? No, it did not need black holes. So that's good, right? It didn't lead to black holes. Now, Einstein A, this is basically Einstein A is concerned with point particles. It's all theory of point particle interactions, which is not reality, no. Point particle interactions. Now, the idea that this required dark matter, well, the idea that omega naught is 1, i.e. that the universe is a special density, was actually imposed on this theory. It's not a requirement of it. Observation is omega naught, if you assume there's no dark matter, is omega naught is about 0.05. Okay? And I wrote a second paper which involved that. But the Einstein theory does need dark matter to keep galaxies formed, to hold them together. It needs it. And it hasn't been found. So there's a big problem with Einstein A, which I said is about point events. Does it give us angular momentum of galaxies? No. Nothing in particular about that. Can it predict their sizes? As far as I can see, no. Does it give line structure in the universe? No. Does it give voids? No. Does it satisfy Mach's principle about the distant matter giving us a local frame of reference? To that I'm not sure. Maybe it does, maybe not. Black holes, though, is a big problem. It demands black holes. We've got to have black holes, they've got to turn up because the equations say, well, the equations say there's a singularity. End of the problem. There will be, end of the story. We'll have black holes and we're all going to disappear down them. However, what about Einstein B? Now, Einstein B is little discussed. And when I mentioned this, was it 2 days ago, and I talked to Dunning-Davies afterwards, he said, oh yes, Piers, were you referring to Annals of Physics? Sorry, Annals of Mathematics 1939. I said, yes. So, you know, he knows all these goddamn things about these most obscure papers, and I was duly impressed. And he said, oh, that's the one that says gets rid of black holes, isn't it? And I said, well, I think so. And then I flashed through it and said, yes, it does. And I read it out, and this is the bit I read. This is by Albert Einstein, printed October the 4th, 1939, just before, or was that after the outbreak of war? I'm not sure, actually. After? Must have been printed on brown paper then. Of course, the Germans still use normal paper then, don't they? Who won the war? Don't answer. Right. The essential, this is Einstein in his last paragraph but one, the last paragraph of Science actually, the other one's about thanking people. The essential result of this investigation is a clear understanding as to why the Schwarzschild singularities do not exist in physical reality. So he's telling us they don't exist. But you see, this bit is ignored. People are just forgetting about it. And this is about Einstein actually thinking, look, the points aren't good enough, we've got to move to extended matter. This approach is necessitated by recognising the existence of extended matter. Well, that is reality, is extended matter. Okay, carrying on. Although the theory given here treats only clusters whose particles move along circular paths, it does not seem to be subject to reasonable doubts that the more general cases will have analogous results. The Schwarzschild singularity does not appear for the reason that matter cannot be concentrated arbitrarily. And this is due to the fact that otherwise the constituting particles would reach the velocity of light. Well, you can argue about his reasons, but the point is the conclusion is something that's not well known. So, if there's any good thing in general relativity, it's going to be Einstein B, which is probably more difficult calculations than Einstein A, so that's why they don't bother about it. Okay. Right, now I want to give a quick applause to Einstein B, because I think he was... Right, now we'll have Mike McCulloch, quantized inertia. If you recall, he said, look, in the kind of universe there's these sort of waves that happen between things, and it's like ships in the sea. And if two ships are close together, there's waves outside them and there's waves in between them. But the waves in between them will have to satisfy harmonics to get the same whole numbers between them. So big waves can't be there, but there can be big waves outside that can So the result is that ships get pushed together. So that happens in the universe, he said, so this becomes a kind of repulsive force between the distant universe and objects. So this turns into then, you've got a 1 over r squared force in gravity. He doesn't talk about ordinary gravity, and there's a kind of 1 over r force that comes from this quantized inertia. Now, this is all hand waving, if you like, but you see the results that come out are pretty smart. Does he need dark matter? No, he doesn't. It isn't anything that comes up a problem. Does it deal with galaxy angular momentum? Well, it probably is okay on that. I don't know. But it does give galaxy sizes very definitely. Because if you've got an inverse square force, A over R squared, as you go outwards, a B over R force will dominate. And at some point, A over R squared, well, when B over R takes over, then you're going to have a different scale. So when they're equal, that will give you to define the size of the galaxy, which means all spiral galaxies have got to be about the same size, because the A's and B's are going to be universal constants. Okay, well, all spiral galaxies are about the same size. So this is pretty clever stuff. Does it give galaxies in length lines and voids? He doesn't answer that, doesn't say that. Does it agree with Mach's principle? Absolutely it does. Mach's principle is 100% written all over this. The distant universe is telling us what is the local inertial frame. That is tremendous. Does it have black holes? No, it doesn't. Mike McCulloch dismisses, or it's quantized inertia, the name of his theory. He doesn't. Black holes are just stupid, he says. Right, and the electric universe theory. Ta-da! What does this do? Well, just a sort of word of kind of, not exactly a warning, but a point that Wald says is wrong and unsatisfactory about standard electrodynamics, etc., is that the force of an electron, if it's in an oval shape around an atom, is going to be directed backwards because there's a time delay. Now, that's kind of okay. However, you see, as I mentioned before once, electromagnetic theory gets rid of that problem by making a different variable for momentum. It has an invariant momentum, includes electromagnetic momentum. So the proper conserved quantity of momentum in an electric or magnetic field is P, momentum, plus Q times A being the vector potential. So the way it all works out very cleverly is that the rate of change of A will give you a different force, and you add them together and you get something that is in the same direction as the instantaneous force. So it's very clever stuff. Very clever. It could all be a trick, but it is clever stuff. And you know, so the point is, when we say they're wrong, it's best not to say they're wrong in a way where actually they might be right. But I mean, probably everything else you say is completely correct, citizen. Right, okay. Will we get angular momentum galaxies out of electric universe? I would say very likely we will. And I was very impressed by that young guy here doing about the lines of galaxies. He's not here today, but very impressive stuff he's doing. And I think we should work with him, and I think he might get that. Will he give us sizes of galaxies? I don't know. I don't know. But when you're talking about scales of Ibex and so on, you know, maybe we could get there. We've got to have arguments as to why the scales are they are. But, you know, I'm more optimistic that it'll work there than the cosmic superstring or Einstein A, for example.
There is a scaling.
Yeah, there we are. There we are. You heard it. Do we get lines and voids? Yes, we get lines and voids out of the electric universe. They follow automatically. Is it in accordance with Mach's principle? Well, that isn't there yet. I don't know. I don't know. I mean...
Yes, it does.
Yes, it does. Well, there you are. He would say that.
It's crucial.
It's crucial. Oh, yeah, well, in that case, I'm going to applaud you now. Applaud you now.
Our universe connected.
Right, and does it need black holes or lead to black holes? No, it does not. So
Stop swearing.
it's good. So of all these things, I would say, although I did sterling work on the Higgs-Kibble cosmic superstring theory, I think that has got limitations. And you know, the best things in here are Einstein B and the electric universe. So I'll end there. Thank you.
And on that happy note, we can stop for supper.
Questions, because questions will go on forever,
Oh, yeah.
so maybe we'll
Yeah.
Well, do you want
ask
any
you over
instant-
tea.
Pardon?
We can ask you over tea.
We could, yeah, whatever. What do you want to do? Do you want to stop now?
I don't know, I think everybody's had quite a long day.
Yeah, Zonta, discussion later. Discussion up here. Oh, copies of these 2 papers I wrote, people can come and collect.
Thank you.
Thank you.
Where do we collect?
Yeah, Mark. Yeah, come here and I'll give you. Well, I've got to make sure that Paula's got. You've had. I don't know what I've given you, Walt. I frankly don't remember.
Yeah.
But I've got